Welcome friends, I am Tanmay. I welcome you all in my channel Chemistry and History of Molecules. So today we will discuss a redox reaction which is named as Bouveault reaction. What is the uniqueness of this reaction? This is the reduction of carboxylic ester into alcohol. So today's topic will cover few points. For example, the basic concept of this reaction, the redox centers and redox changes. After that, we will discuss about the role of reagent like sodium, alcohols, mechanism of this reaction, and proof of mechanism. What we are saying, what is the support, and most importantly, I will provide some reference in the comment box. Please see those or verify or check those reference if you want to cross check. And finally, some related reaction about this, and then during this time I'll explain about the next video. Okay. So let's start. So this reaction, as you can see, this is Bouveault reduction, means the reduction of an ester. This is ester of an carboxylic acid. Ester to alcohol. When we say this ester to alcohol reduction, instantly one word comes in our mind. What is that word? That is lithium aluminium hydride. Lithium aluminium hydride. Okay, so this lithium aluminium hydride is a very good reducing agent to reduce ester into corresponding alcohol, but they are relatively costly. Okay, and when this reaction of lithium aluminium hydride, this thing was not developed, that time this Bouveault reduction was one of the choice, means very important, or you can say very reliable only process for this reduction. Okay. Second, what reducing agent we are using? We are using as a reducing agent as metallic sodium. As we know, using Kastner method or Downs method, we can prepare sodium from, means using one method we can prepare from sodium chloride solution, and another method we can prepare from direct molten sodium chloride. Okay. So this is easy to prepare because electroreduction resulted into that corresponding metal. Now, as you know, the group 1 means lithium, sodium, potassium, etc. This is group 1. They have lost one additional electron in their outermost valence shell, and which if they release means form this plus, and they get nearest noble gas configuration. That is the reason they are so much prone to give electron, and that is the reason that they are very good reducing agent. Why? Because they are interested to release one electron, and that electrons they like to give. They are not comfortable with that electron, extra electron. So they want to give, and they need someone who can accept, and in this case ester is doing that, ester is performing that job. Now when we say that this is a redox reaction, so simply you will ask, okay fine, that sodium is getting oxidized, sodium 0 to sodium plus. Now question, who is getting reduced? Sodium 0 to sodium plus 1. Who is getting reduced? This carboxylic ester. How it is reduced? If you see here, this carboxyl carbon is in plus 3 oxidation state, and after reduction in presence of the electron coming from this sodium, it is reduced into -1. So what is the extent of oxidation number? Means number change, you can say that plus 3 minus of -1, so it is a 4 electron reduction process. Okay, so 4 electron needed to perform this reduction. So this 4 electron process. Now question, this 4 electron must be supplied by the sodium in order to have a complete conversion. It is, and that's why 4 equivalent is essential. But why I have written 4.5? Because whatever solvent we use, anything moisture, so that is there, means responsible factor is water. And if you compare the reactivity of water versus alcohol, for example, let's consider ethanol. So water is more reactive, okay, more polar. This OH bond is more polar, because if you see this electron difference between oxygen and hydrogen is more compared to this carbon and oxygen. That's why this bond is little less polar, less reactive. And another thing, stabilization of the final cation is also important, and in that case water is better compared to alcohol. So reactivity of sodium is more, so slight excess is needed. I'll provide some reference, so you'll have idea. Now there is another problem, that use of sodium is hazardous, because this is a very reactive and sometimes there is a chance of catching fire. So first of all, reaction must be carried out under controlled environment. Second, we must be careful. And third, if still problem persists, there are some solution, like instead of metallic sodium we can use sodium in silica gel. This silica gel acts as a matrix for the reduction of reactivity of metallic sodium. So due to this modification, we can expect the reactivity of sodium is controlled right now. So right now the reaction is little more safe, you can say, because if we can't control a reaction, that may create many problems. Okay, so this is the role of sodium, what we have done. Now the role of alcohol. When you see an alcohol, then a question may come, that we have read sodium plus ethanol ultimately produces sodium ethoxide plus hydrogen. It's true, but fastest step is electron transfer, and due to electron transfer this reaction happens. What do I mean? Sodium produces this sodium plus and electron, and that electron actually reacts with this OH bond. So first electron release happens. Okay, so that's why that we are using alcohol here. It's true, but it is not directly producing hydrogen. Instead of that, what alcohol is doing here, ethanol or alcohol, means it is better to write general name. Alcohol is acting as proton supplier. Okay, so you may be confused that why this is. I'll put proof that alcohol is acting as reference. Okay, so this will be helpful to get. And the final step is workup, which results in this. Okay, so we have discussed the role of sodium and alcohol. Now let's discuss about the mechanism. So as you can see, this is a dissolving metal reduction. You may consider like Birch reduction we have read, and in this context I want to say, you previously I have uploaded a video about Birch reduction. Please see actually not one video, 3 videos. Birch reduction for aromatic hydrocarbons, Birch reduction for electron withdrawing and electron donating substituents. Okay, so I suggest you please go through those videos first. After that we will discuss go through that videos also. That is helpful because that is also sodium dissolving metal reduction. So now fine, we have understood this part. Now let's go to mechanism. Mechanism in first step, sodium means sodium is converted to sodium plus electron, and that electron actually attacks this carbon. Why? Because we know this ester, this R1 and R2 different. You can take same for generalization. I have taken this. You can consider this is a delta plus, this is a minus, delta minus, or you can know that there is a canonical form, that R1 CO minus carbon plus and OR. Then this oxygen helps and reduce. So in this way this goes on. So what is the summary of this statement? Summary of this statement, that this carbon center is electrophilic, or you can say electron deficient. If it is electron deficient, now you can think that okay, there is excess of electron, so this excess electron can go and attack on this center. Fine, and that's actually happens. So the electron, this electron goes and attacks here. For better clarity, I can give you another explanation. What is that explanation? See, a pi bond is made of this carbon and oxygen. Carbon, this is oxygen. Electronegative atoms, atomic orbitals energy is less. So that's why in this way, this is energy. So they forms pi. This is a P. Let's consider this is PZ, this is PZ. Ultimately produces, this is BMO, that is pi bond, and this is ABMO. You can consider this is a pi star. Okay, so one electron from here, one electron from here produces this. So where this electron goes, actually this is filled. So this orbital is filled. So we know that a particular orbital can hold maximum 2 electrons. So where the electron is going, this extra electron is going to this, means this antibonding orbital. So antibonding orbital, if you provide electron, the bond order reduces. Bond order means that bonding electron minus antibonding electron divided by 2. So right now see, bonding is 2, antibonding 1 divided by 2 equal to 0.5. So means that pi bond is half broken. Okay, and that thing is represented by arrow marking. This convention is that it forms a, means it is not exactly ketyl radical type, I should say. Okay, if it is ketone, then you can consider this is a ketyl radical, but this is like that. This is the radical. Why? One electron went here, so this bond opened up, ultimately produces this. Okay, so this is. Now in next step, what is done? Since we have used as ethanol, means for example, let's consider instead of alcohol we have used ethanol as a solvent. Then this ethanol acts as proton donor. Proton donor to this, because actually one thing keep it in mind, there is sodium plus, so E2 will remain closer to this in order to maintain the electron neutrality. Now this will abstract this proton. So what is the thing? R1 C dot OH OR2. Fine. Okay. So this is produced. Now after that it abstracts this sodium to sodium plus electron, and that electron again attacks here, because this is a radical. What do I mean? This radical means this is a 7 electron species, and it is electron deficient, because we know that a particular atom electron deficiency is neutralized when it has octet. Right now this doesn't fill this octet, so it is expected that since it is not octet filled, so it will take another electron, and what it will do? This will do C minus OH OR. Okay, in this context I want to mention, since it's a radical, you can say this hydroxyl attached to its radical or is radical anion. How this is stabilized? This is stabilized by resonance. What type of resonance? What type of resonance? So this is carbon having 1 electron, this is oxygen having 2 electrons. You can't directly show it based on VVT. You have to discuss this based on MOT. This is the energy, this is the carbon, this is the oxygen. So they can overlap to each other to produce this and this will do. Now the question, why this interaction will happen? Actually the driving force of every interaction is stabilization. So what type of stabilization is available here? Actually you can see these were near about the barycenter, means the level of p orbital, 2 stabilized, 2 stable, 1 unstable. So now need 1 stable, and that is the way this radical is stabilized. Keep it in mind. But when there is another electron, so what will be the consequence? So here another electron, anti-bonding. So at this case, right now, no stabilization, or it is better to say some amount of unstabilization. Why? Because see, this we know that the stabilization of the bonding orbital, and this, if we consider this part as delta E1 and this is delta E2, then this delta E1 slightly greater than, actually slightly greater than, I repeat, delta E2. Consequently, unstabilization is more. That's why. Unstabilization is slightly more than stabilization. So, this is not stabilized. That's why I say no stabilization. Fine. Now the question, then what happens? This is actually pure lone pair, this has lone pair, this so severe repulsion occurs. And consequently what happens? Due to this repulsion, this carbon ion, actually this is a carbon ion right now, this carbon ion is very reactive and ultimately result in protonation. And protonation from whom? This ethanol molecule. Okay, so ethanol is converted into ethoxide and this is converted into reduced protein. So this is OH, this is H and this is OR. Fine. Actually see now, right now this carbon is reduced. Actually we are focusing on the reduction of carbon center because the oxygen is not reduced. So what happens now? This is a hemiacetal type. Okay, this is nothing but you can consider this is a hemiacetal. Means hemiacetal or you can say semi-acetal. In future I'll describe this hemiacetal thing in another video. So this is a semi-acetal. So what happens? It pushes and it lifts. And hemiacetal are both acid and base stabilized. How? See, base means in medium there is a ethoxide. There OET minus. So it attacks, abstracts this proton, means it comes back and ultimately it leaves. So ultimately what will be the product? In this way this will produce R1 C double bond OH plus OR2. Okay. So and what will be the consequence? Then this will react, OR2 minus. Okay. So after that what will be? This aldehyde, it can further reduce. And another thing, this is not completely reduced, it's intermediate from like that we know that alcohol to aldehyde to carboxylic acid reverse, the carboxylic acid or ester to aldehyde to alcohol, this is an intermediate state. Okay, this is the intermediate. So what happens with this? This further react with the electron from this sodium. Similarly, it opens up. So what is produced? So this is R1. This is you can say ketyl radical. Means aldehyde. Actually, ketone it is ketyl radical, aldehyde radical. So ketyl radical type. Ketyl radical. Okay. So this is, and next step what happens? It takes another electron from another sodium because this thing similar mechanism. This abstracts proton from alcohol. It abstracts then another electron to prepare itself carbon ion, and this carbon ion abstracts another proton from water molecule, ethanol as a solvent, and ultimately this thing is produced and this is the alcohol. Okay. Now question, we have found that two types of alcohol produced. So where are these two types of alcohol? Type 1 and type 2. So when this elimination was happened, along with that it produces R2O minus. This is alkoxide, and here actually ultimately it will remain as not only this OH, ultimately it will remain as O minus. I should say this is the plus. And during workup with H3O plus in the next, after completion of the reaction, workup is essential. That time it will produce that corresponding alcohol. What do I mean? This R1 CH2OH, and from here if what it will produce? R2OH. Okay, see, this is done. Okay, now fine. We have discussed about the mechanism. Now our time is to discuss about the proof of mechanism. Okay. So proof is that instead of ethanol, if we use deuterated ethanol, what do I mean? C2H5OD. This is deuterium. This deuterium is nothing but the isotope of water. What do I mean? This D, deuterium, its thing is that one proton and its mass is 2 because one neutron is there. Okay, as compared to hydrogen, this is 1:1. So this is deuterium. So if we use deuterium, ultimately what we get? If it is this C2H5OD, the product we get R1CD2O, and whatever acid that will be, if it is H3O plus, then OH, and this is R2OH. That proves that alcohol is acting as a proton donor because the OH, this is coming from this H3O plus, so no problem, fine. But this is how. See, at this, when the reaction happened, this is instead of this OH, if we write D. See, here, instead of this H, if we write D. So, what will happen? That you can, first of all, you can think there is D, no problem, fine. I'll explain, ultimately it will not be there, fine. After that, this electron, this reduction, this is carbon ion. So, if it is ethanol, means D, then this is D, fine. So now see, previously whatever you expected it is D, this D is abstracted by alkoxide. So again it will produce alcohol, means deuterated ethanol. So fine, now this is D. Okay, again electron reduction, this is O, and so reduction means there will be an anion produced, and that anion will abstract proton from deuterium. So consequently, previously there was one D, right now there is another D. So ultimately now this will be CD. Okay, so this is the proof of mechanism. I will provide the link of this, so you see. And so proof of mechanism we have discussed. Now related reaction. So there is another type of reaction using this sodium alkoxide in ester. Similarly, so instead of polar proteic solvent, if you don't use any polar proteic, instead of that, if you use aprotic non-polar solvent like benzene or xylene, means this is toluene, and xylene is 2-methyl. Okay, see, this is methyl, let's consider another methyl here. So different aphthosylene, paraxylene, such type of thing. It produces Acyloin, and that reaction is called Acyloin Ester condensation. Okay, in the next video I shall explain about this Acyloin Ester condensation. So these are the related reaction. Okay, so what we have learned today? We have learned about this Bouveault reduction, which is an efficient method for reduction of ester to corresponding alcohol prior to lithium aluminum hydride that time. So another thing, we have discussed about the basic concept, mechanism, and the proof of this mechanism using this deuterated ethanol, this thing. Please keep it in mind, this is an interesting thing, it will enrich your knowledge. And last we have discussed about the corresponding aprotic solvent derivative, that is this. And in case of this, you can see when there is a polar protic solvent, then this prepared anion, this prepared radical is further reacted with this and ultimately produce anion. But if we use this xylene, this radical can dimerize. This dimerize to acyloin. Okay, in next video we will understand that thing properly. So this is the uniqueness of this polar protic solvent. It stops the dimerization also. And finally we get the alcohol. So this is the end of the video. If you like my teaching, please subscribe my channel Chemistry the Mystery of Molecule and share this video among your friends so that many people could be benefited from my effort. And more importantly, please press the bell icon to get the notification of every single video I upload. Additionally, if you have any query, suggestion, confusion, please inform me in the comment box. I'll try to answer as much as I can. So this is the end of the discussion. Thank you everyone for listening my video. See you in my next video. All the best. Stay happy. God bless you.